Let's see. Okay. All right. We'll start here. Let's see. All right. So welcome. We are at. Let's see. So this is the top of week 6, right? So I hope that everyone had enjoyed your weekend, right? So you got some rest and did what you needed to do, had some fun, and balance between doing what you want to do and what you needed to do. So the structure for our course, going forward, basically we do 3 weeks of lecture and then 1 week of testing, 3 weeks of lecture, 1 week of testing, 3 weeks of lecture, 1 week of testing, right? So with this being week 6, that means that we can anticipate exam 2 to become available in basically during week 8. And exam 2 is going to cover the material from weeks 5, 6, and 7. Okay. The main things that we need to make sure that we're getting done is 1, our assignments that are on Pearson, right? So we're making our way through that stuff. It's basically 1 section every week. It's not a lot of work, but you don't want it to pile up if you haven't started already. And with Pearson, we get unlimited attempts at all assignments. You can submit any assignment late with only a 10% late penalty all the way up to the very last second. And there's only a 10% late penalty. And I think the system is set to take your highest score. As a reminder, this is remote online asynchronous. So if you're in the Zoom call right now, you've gotten your attendance credit for the day, and you're not obligated to stay. And let me see. So, we're going to kind of continue where we left off last time. Let me see what section we're talking about today. So we're continuing chapter 1 and working on section 1.5, transformations of function. And this is an extension of, basically each section is building on the previous, right? So last time, I think we did section 1.4, that was a library of basic functions. And, we had these lists of different functions. Now, I think together we got through as many as we could, but I want to say that in my pre-recorded lecture, I went further into detail and I did the whole section, right? So, we have 2 50-minute sections where we meet together. That's not really enough time to do everything. So that's why I built so much stuff to be done outside of class. The original intent was for this time to be like a Q&A or a study session or office hours. And I just fill it with the lecture and homework just so that there's not dead air. So if anybody wanted to work on like some homework or something else, we can work on it. Otherwise, I'm just going to make my way through as much of the lecture as I can. Okay. As usual, if you have questions, feel free to unmute yourself to get my attention, or type in the chat. I do check the chat periodically. And I'll be checking the attendance again around 3:15 to get any stragglers, right? So that's usually what I do. It's like right at the start of class, I'll take attendance. And then after I finish that first wave, then I'll check it again around 3:15. Otherwise, it's like a lot of back and forth. And this was eating up a lot of time. Is what I noticed in the past. So that's why I do it this way. Otherwise, because people kind of trickle in. The best practices, you definitely want to be in the waiting room about 5 minutes before the start of class. Because I stopped checking. Like once I do that first wave, starting at like right at 3, then I stop checking it after that. I don't check it again until 3:15. And sometimes I go over. Oftentimes I go over. But anyway. Okay. So with section 1.5, we have transformations of functions. So a few objectives. We like to define transformations of graphs, use vertical or horizontal shifts to graph functions, use reflections to graph functions, and use stretching or compressing to graph functions. Also, so not only make sure that we're making our way through our material on My Math Lab, but I think this class also has a lab. So, each person should have by now contacted Dr. Lamar, and, her contact info is on our Blackboard page on the left-hand panel. You reach out to her and basically follow her instructions. And about the midterm and the final, she's going to give me a grade for each student that has a lab. And I'm just going to take that grade, whatever she gives me, scale it to 10% of your overall grade and incorporate it into your midterm and your final. The only grade that really matters is the final. So when the midterms grades are released, those are just, the midterm is, all it is a snapshot of where you are at that moment in time. It has no bearing on your final grade, right? So it's just like, okay, well, this student let's check on this student, see where they are, or this one has the rhythm. Now we just want to encourage them to maintain and maybe help others, this, that, and the other, right? So that's what the midterm grade is. But we'll talk more about that as we get closer to it. Okay. So then we have transformations. If a new function is formed by performing certain operations on a given function f, then the graph of the new function is called a transformation of the graph of f, right? So we're going to start with this basic function, absolute value of x. This is kind of cut off. Let me go back. This is what, 3 o'clock? Just this one? There it is. So we're starting with the basic function, absolute value of x. And then g of x is going to be absolute value of x plus 2. And h is going to be absolute value of x minus 3. We're going to sketch the graph of these functions on the same coordinate plane and describe how the graphs of g and h relate to the graph of f. Okay. Can anybody tell me what is the basic shape of this graph here? We have absolute value of x. What's that? What's the basic shape? Absolute value of x. So absolute value of x makes a v, right? So then if we're going to start with a v, we're going to see what happens when we add 2 on the outside. We add a positive on the outside of our basic function, and we subtract a positive on the outside of our basic function. So we're going to basically make a table, choose several values for x, find the corresponding f, g, and h, and then plot these 3 graphs on the same coordinate plane. Okay, so make a table of values and graph the equations. So on the left-hand side, you see several values of x here. And then we're considering absolute value of x. So absolute value is the positive distance away a number is from 0. So for instance, the absolute value of -5 is 5. So on and so on. So absolute value is the positive distance away a number is from 0. So then for this absolute value of x plus 2, basically we're adding plus 2 to each y value. All right, so on and so on. All right, we're just adding 2 to the y values. So if the blue is our original, can anybody describe to me how do we go, what kind of change happened when we went from the blue to the red, when we added a positive on the outside of our basic function? Notice that our x values stayed the same, but the y values went from wherever they were, and they basically went up by 2. So adding a positive on the outside of our basic function caused our original graph to shift up 2 units. So if adding a positive on the outside caused it to shift up, what do you think subtracting a positive on the outside causes? Right? And that's where this comes in. So I think it still has the same precursor, several values of x compared to absolute value of x. Now we're going to subtract 3 on the outside. So that's like subtracting 3 for each y value. So if we said -3, -3, -3, -3, so on and so on, right? Subtracting 3 from each y. So then when we plot all these ordered pairs, the blue is our original graph, and we went down by 3 units. Right. So to kind of recap, all right. So to kind of recap, adding a positive outside our basic function caused the original graph to go up that many number of units. Subtracting a positive on outside of our basic function caused the original graph to go down. Okay. So for vertical shifts, given some positive number, y, when we take our basic function plus that positive, is going to be our basic function shifted c units up. If we say our basic function minus that positive, it's going to be the basic function shifted c units down. Okay, so outside manipulations typically cause a vertical change and it follows our intuition. So if outside manipulations cause a vertical change, what do you think an inside manipulation might cause based on that primer? Okay. So in this example, we're considering the basic function x squared, right? Hopefully in your mind, you should be thinking like a U-shaped graph, all right? So then if we subtract 2, hang on. So if we subtract 2 on the inside of our basic function, we're going to consider what happens when we subtract 2 on the inside of our basic function and we add 3 on the inside of our basic function, right? So we're starting with a U-shaped curve and then seeing what happens with these two manipulations. Give this one a go. I'll be right back. Give me just a moment. All right. So yeah, sorry about that. I'll check attendance in just about a minute. Okay. So with this one, it's kind of a repeat, right? We're going to make a table of values, choose several values of x, plot the corresponding y corresponding to f, g, and h, and then compare and contrast, right? So we have our several values of x. Passing it through the function x squared, you get these results. Then when we subtract 2 on the inside, the first one ended up being 36, then 25, so on and so on. And then notice it repeated when we got to 16, all right? So that result appeared two steps down on this graph, right? They all kind of shifted down by 2. This one shifted up by 3 in this fashion, okay? So then when we plot all these ordered pairs, let's take a look at the graphs. So the blue is the original. Now, when we subtracted the 2 on the inside, notice it moved the original graph right 2 units. Okay. With the red, when we added a 3 on the inside, it shifted it to the left 3 units. Okay. So what this is showing us is that inside manipulations typically cause a horizontal change and is the reverse of our intuition, right? Because you might think that, oh, a -2, we go -2, but actually that's not the case. It's the reverse, right? And so the way I kind of remember that is I ask myself, okay, well, what value of x, when I'm working on the inside, I know it's the reverse of my intuition. So I ask myself, what value of x makes this inside part 0, or what's my x-intercept, right? So then +2 is my x-intercept, so I went to the right by 2. Okay, let's use this slide. So all 3 functions are squaring functions. G is obtained by replacing x with x minus 2. So then for the basic function, the x-intercept is 0, but then when we have the x minus 2, the x-intercept is 2, all right? So for each point x, y on the graph of f, there will also be a corresponding point x plus 2, y on the graph of g. So long story short, the graph of g is f shifted 2 units to the right. So this -2 caused the original graph to shift to the right by 2. This positive 3 on the inside caused the original graph to shift 3 units to the left. Okay. So to kind of recap, so we've talked about, so far we've talked about 4, I'm about to check the attendance in just a moment. We've talked about 4 transformations. The first 2 were vertical. Adding a positive outside our basic function caused the original graph to shift up that many number of units. Subtracting a positive on the outside caused it to go down. Adding a positive on the inside caused a horizontal change and was the reverse of our intuition. So it caused it to go to the left that many number of units. And then subtracting a positive on the inside caused it to go to the right. Okay. Let's take a moment there and see if we have any stragglers. Okay. That is fine. So let's go here. This one. Okay. All right. Oops. All right. So now, I just checked the attendance. Like, only people that were there were the latecomers, and I had one student that was hanging around. So now, just be aware, things like this, it just kind of creates, it just doesn't look good. You know what I mean? It kind of creates this image.
Well, because I joined early, but I don't think you let me in.
Not you guys. I'm not talking about you guys. I'm just.
Oh, okay. I was confused. I was like, I think I joined.
No. So basically, I'll check it like right at 3, right? And so I think I stopped at like 3:03, and then I don't check it again until 3:15. But I'm just talking about there were like, it was a good amount of people that were here, but this is okay. I'm just saying it just for it to be on record. It just doesn't look good, right? But it's okay. It's nothing wrong with it, but it does kind of influence like further down the line when I'm like, okay, it's at the end and people are asking favors and asking for this. Can you do this and that and the other? I'm like, yo, I haven't seen you all semester. Where have you been? Like, that's all that's going to be in my mind. So it makes it a lot harder for me to be cooperative. You see what I'm saying? It's just an image. Even if you just sat on the call and was like mute, I feel like that still looks a little bit better. But it's okay. It's not anything. I'm just like, it just kind of creates this thing. But again, this is remote, online, asynchronous, so it's okay. It's like you can, as long as you have a plan or a way to kind of get what you need. For right now, I mean, for our purposes, I am the authority on it, but I know that my energy kind of drones, and it's. I remember that experience, like when it's just, math kind of has that nature about it. Just like the intimidation, or what, I don't know what the word is, but that feeling of like going to the professor, it can be a challenge, right? Because not too many people ask questions, but I'm like, okay. And this stuff starts to rev up. It's gonna rev up. Like whatever we've been going over so far, I don't know how it's been for each person, but as the semester goes, I mean, it just keeps piling and piling and piling. So I'm hoping that people, which this happens time after time, but and I hope that people aren't just procrastinating and sitting by. At least try to get yourself submitted. If you gotten yourself submitted already and you're just waiting on the exam, that's one thing, right? And I know there are some people that do that as well. My personal struggle is not assuming the worst. Like, let me just give them the benefit of the doubt and let's see where the cards fall, because that has happened as well, where I had this like negative, nefarious sensation. I'm like, okay, where are these guys? What are they doing? But then when I check them, they're actually okay. Like, they've submitted their stuff. They're just waiting for the exams. Like, okay. And it actually works out. And it's not like everybody like blows it out of the water. I mean, it's an actual spread where some people got A's, B's, C's. It's a whole, so I was like, okay, it's fine. But I do encourage everybody to kind of work together. Like, I think that's a good idea. Just, if you have some kind of accountability buddy and to help you be accountable for yourself, or you've linked up with the tutors, it's okay. Like, it's definitely encouraged. Okay. So we got these 4, but yeah, if you're just joining us, it's okay too. Because again, I don't check it again until about 2:15 or the 15-minute mark. I mean, Okay, so we're working on section 1.5, and we've gone through, I think, like 4 transformations now, right? The thing with this section, the concepts are not difficult, but it definitely can be information overload. And so like what happens a lot of times, a lot of students get caught lacking. And what I mean is that they get like overconfident and they think it's like this, that, or the other. They procrastinate, and then when it comes time for them to do what they need to do, it's like brain fog, right? So that's what I'm trying to avoid as best I can. But again, I can't make you guys do anything. I just set up the stage and make myself available and just try to encourage you, right? And again, students make their own plans and it works, like for them anyway. They get what they need out of the experience. So I just have to kind of trust it and let it go. Let it go. Sorry, give me a moment. I've been talking all day. I don't get it well. I don't want to talk. So I'm trying to wet my palate. So it's not, my mouth isn't so dry. Luckily, before you guys, I took a nap because the class before you, I was like a zombie. I'd be like, it used to be worse when I was in person too, because I would still be sleepy. And like there were times I'm trying to lecture and I'm falling asleep on my feet. And I was like, man, I just want to lay down and like take it down. So I was like, okay, I went on and gave myself a little bit of cushion before you guys. I took a quick like power nap. I feel good. Okay, let me see. Oh, maybe we haven't talked about horizontal. So we've talked about 2. We talked about vertical shifts up and down. Let's look at and we've talked about horizontal. This is just a formal, this is like a more articulate way of saying what we said a moment ago. So let C be positive, then the graph of y equals f of x minus c. Notice we're subtracting a positive inside our basic function. Is the graph of the original shifted c units to the right. See, it's the reverse of our intuition. And then when we add a positive inside our basic function, it's the original function shifted c units to the left. Outside manipulations are typically vertical changes and follow our intuition. Inside manipulations are typically horizontal changes and they're the reverse of our intuition, generally speaking. Okay, so in this example, the axis is to sketch the graph of the function. Sorry, I keep thinking like, and again, don't get too caught up in, I'm an emotional being. I can be very emotional. And so like part of my challenge is like, I acknowledge my emotions, but I try not to like subjugate others to my emotions. I still try to be as fair as possible and like as patient as possible because I can be not patient. So that's why I be like laughing and I try to make everything as light as possible because one, the nature of mathematics is just a beast by itself. And then you don't want to throw my emotions on top. That's not the place for that. There was something else I wanted to mention there. So with this one, so yeah, like my complaining, because I kind of mentioned this with my students earlier, where whatever we practice, we get really good at. And I was like, yo, I'm the king of King Charles, not the Queen. That stuff in England, that stuff is wild. That's sparking this huge debate as well, where people keep some people are like, I hope she suffers, and I'm like, what? But then when you think about their argument, I mean, I get what they're saying, so I'm just like, it's tough. That's a tough one because it's still a being, it's still a human being. You don't want anybody to suffer, but if you think about all the stuff that they allowed and the atrocities that they, allowed to happen worldwide against other people, I see where they're coming from with that, But coming back, I'm the king of complaining and procrastination. So I was sharing with my students earlier, when the challenge I've given myself is when I realize I'm complaining, that's just saying, hey, that's something that needs your attention. It's nothing, because complaining doesn't do anything. It doesn't fix anything. When I'm done complaining, it still is the way it is. It's not until I take action and I do something about it that it actually has effect. So when I realize I'm complaining, I just have to pause for a moment and say, hey, that's just something that needs attention. And because I notice it, I need to be the one to do something about it. You do something about it. You know what I mean? But complaining in and of itself doesn't fix anything. It's an alert. It's an energetic alert. So, and then also just being the king of procrastination. that never really pans out that well for me either. I always do better the earlier I start. That's why I kind of set up the class the way it's set up, where the homework was available from the rip and the quizzes were available from the rip. I try to make as much stuff available as early as possible. Okay, so that was that whole backstory. Anyway, so in this example, we're actually sketch the graph. So basically, this is like a fusion of 1.4 with the library of functions and incorporating, we got two transformations going on here. So we have this basic function of the square root of x. Square root of x, right? I'm having a lot of internal dialogue, not about this. Cause like now I'm thinking like, if we were in person, I would be looking face to face, look you guys in the eyes and like, hey, trying to get feedback. And then I was like, well, what if I tried to have them, have the video on during class, but then I'm like, well, then they can make one of those fake things that loops, and just still blank out. I was like, no, forget it. So I was like in that little moment, I was going down this whole little random path like that. So that's why I started giggling because it was funny to me. So the basic function here is square root of x, right? So the way I remember the shape of square root of x, to me, it looks like the top half of a sideways parabola. So if you take a U-shaped curve, turn it to the right by 90 degrees, cut it in half horizontally, square root of x is going to be the top half of a sideways parabola. That's the general shape of square root, right? So then when we're doing multiple transformations in one function, the recommendation is we want to work our way from the inside to the out. So the innermost transformation is this +2, right? So inside manipulations generally cause a horizontal change and is the reverse of our intuition. Our intuition might say, oh, this goes to the right by 2, but this is actually the reverse. So instead of going to the right by 2, this one says go to the left by 2, right? So this is a sentence. This is telling us about the shape of the graph, right? So it's basically saying, come on, let's choose this color. We're starting with square root of x, right? Which is the top half of a sideways parabola, kind of like this. And then that +2 tells us to go left 2 units. And then that -3 tells us to go down 3 units. Right? So those are the 3 transformations. And basically we're kind of following this point here. And it just goes left 2 and then down 3. And that's going to be our graph. And then once you kind of get the sense of those transformations, you can confirm it by plotting points. Choosing several values of x, find the corresponding y, plot the points. And if you follow that original point, it'll go left 2 and down 3, and it should be that graph, right? So we chose the basic function of square root of x. All right, our c is -2, so that tells us to go left 2. Our d is -3, so we go down by 3. And they basically converted it to this form here. All right. So notice we had like a +2 and a -3. Well, the general form was x minus c plus d. So they rewrote this +2 as minus a negative. They rewrote this -3 as plus a negative. So then once it's in this form, with the c being negative, that said to go left 2. This one says to go down by 3. That's another way to do it. Okay, to visualize that. So since our c was negative, the graph is shifted horizontally 2 units to the left. And then because the d was negative, you go down by 3. And then you see it here. Top half of a sideways parabola, we went left 2 and down by 3. Okay. I feel like there should be questions, but I also feel like there might be questions, but you don't know how to ask it. Because again, these concepts are like simple, but it is information overload, right? So this is just like one of the ways of graphing. Like honestly, when I was a student, I mean, I'm still a student, but when I was in school, I never took college algebra. I just knew how to do like calculus because that's the last thing I did in high school. And so I knew how to like graph, but I had never seen transformations like this. And I wish I had known it because I could have used it in grad school, but I could still get in the program or something. But I'm honestly thinking about like something else, like architecture. That's the one I'm drawn to. I don't know. I'm going to do something different. Right? Okay. So we saw an example where we did multiple transformations in one go. I think we've talked about 4 transformations. So now let's move on to the next set of 2, where we have the first one is going to be the first of the new set of 2 is we want to consider reflections in the x-axis. All right. So the graph of y equals negative f of x is a reflection in the graph of y equals f of x about the x-axis. All right. So notice we're multiplying the outside by a negative. So it's like we're multiplying the y values by negatives. It's like our y's are going from positive y to negative y, or vice versa. And the x values are going to stay the same. If a point x comma y is on the graph of our basic function, then the point x comma negative y is on the graph of y equals negative f of x. So again, it's like our y's are going from positive y to negative y. Okay. All right, let's keep it moving. So it's flipping vertically over the x-axis. That still coincides with what we said earlier, where outside manipulations typically cause a vertical change. All right. Here's an example. So we have some generic function f of x. So then when we consider negative f of x, it's like the y went from positive y to negative y. So it flipped vertically over the x-axis. All right. So we're going to flip over the x-axis. We can also talk about flip over the y-axis. So now instead of the negative being on the outside, now we want to consider y equals f of negative x, where the negative is inside our basic function. This is a reflection of the graph of our basic function in the y-axis. If a point x comma y is on the graph of our basic function, then the point negative x comma y is on the graph of f of negative x, right? So in this case, it's like our y values are staying the same, but our x's are going from positive x to negative x. So that's causing us to flip horizontally over the y-axis, right? So that gives us 6 transformations. Let me see. So there are 10. There are total. There's 10 transformations. 330. All right. There are 10 transformations. So this is 6. So you have moving up and down for 2 vertical, moving side to side, 2 vertical, 2 horizontal, flipping vertically, flipping horizontally. That brings us to 6. All right. Let's see what else we got. Okay. Let's look here. So explain how the graph of this guy can be obtained from the graph of our basic function absolute value of x, right? So absolute value of x is our v. Okay. So let's kind of take some notes here. So then again, absolute value of x, that's a v where the vertex is at the origin. Now when we're identifying our transformations, the recommendation is to work our way from the inside to the out. All right. So the innermost transformation is this -2. That's the nested most transformation. So then if we're subtracting 2 on the inside, our intuition might say, oh, it goes to the left by 2. But remember, inside manipulations are the reverse of our intuition. So that actually says that we should go right by 2 units. Okay. Next, we're working our way from the inside to the out. We consider multiplying by this negative. Kind of like order of operations, PEMDAS, right? So multiplying the outside by a negative, outside manipulations cause a vertical change and follow our intuition. So this is like multiplying the y's going from positive to negative. So the y goes from positive to negative, that means we're flipping over the x-axis. So this causes our graph to flip vertically over the x-axis. And then lastly, we're going up by 3. So that causes our graph to shift up 3 units. Okay. So, when looking at the easiest way to kind of go about it is to follow the vertex. All right. So the vertex starts at the origin, then we will go right 2 units, and then we flip it top to bottom, and then we go up 3. All right. So if you follow the vertex, let's see here. So we started with the vertex at the origin. Then notice we went right by 2 units. I think we said flip vertically. So we just flipped it top to bottom. And then we go up 3 units. So we went right 2, flipped it vertically, and then went up 2. And that was the location of our final graph. Okay. All right, let's keep going. Okay. So this brings us to, we have like 4 more. Stretching or compressing a function vertically, right? So that's 2 of the 4. All right, so we have f of x is the absolute value of x, g of x is 2 times the absolute value of x, and h of x is 1/2 times the absolute value of x. Sketch the graphs of f, g, and h on the same coordinate plane and describe how the graphs of g and h are related to the graphs of f. Okay. Let's do it like this. I'm going to use this color. So absolute value, again, absolute value is the positive distances away from x. We just chose these x values, right? We just chose some x values. Find the corresponding y. So absolute value of -2 is 2, 1, 0, 1, 2. Right? Absolute value is the positive distances, the number is from 0. So then for g, we're multiplying the outside of our basic function by a number larger than 1. So it's like our y's, we're basically multiplying all our y values by 2 in this case. So then that's going to become 4, 2, 0, 2, 4. And then for h, we're multiplying our y's by 1/2. So that's 1, 1/2. That's not a half. 0, 1/2, and 1. So then we want to plot out these ordered pairs on the same coordinate plane. Okay. And this is what we get. Absolute f of x equals absolute value of x. Okay. So when we multiply the outside by a number larger than 1, this red, we call that a vertical stretch by a factor of 2. Like the y values got multiplied by 2. The green, we multiplied the outside of our basic function by a number between 0 and 1. We call that a vertical compression by a factor of 1/2. So we basically cut all the y values in half. Notice in all of these cases, the x value stayed the same. We didn't move it left or right or flip it. We didn't do anything horizontal. You know, these outside manipulations only affected the y. It did not affect the x at all. Okay. So then the graph of 2 times the absolute value of x is our basic function vertically stretched by multiplying each y coordinate by 2. And then 1/2 times the absolute value of x was our basic function vertically compressed by multiplying each of the y coordinates by 1/2. Okay. So the graph of y equals a times f of x is obtained from the graph of our basic function by multiplying the y coordinate of each point on the graph by a and leaving the x coordinate unchanged. So then what happens is we get a vertical stretch away from the x-axis if a is greater than 1, and we get a vertical compression towards the x-axis if a is between 0 and 1, right? We get a vertical stretch if a is bigger than 1. We're multiplying by the outside by a number larger than 1. We get a vertical compression if we multiply the outside by a number between 0 and 1. So outside manipulation still cause a vertical change, and they follow our intuition. If a is negative, then first you just consider where you're multiplying the outside by the absolute value of a, do your stretching or compressing, and then flip it vertically over the x-axis. So if multiplying the outside still causes a vertical change and follows our intuition, so now we want to see what happens when we multiply the inside by these different numbers and see, does it still hold that it's the reverse of our intuition? Okay. So now we want to consider multiplying the inside by a number. The graph of y equals f of b times x is obtained by taking your basic function, multiplying the x coordinate of each point by 1 over b, and leaving the y coordinate unchanged, right? So then we get a horizontal stretch away from the y-axis if b is between 0 and 1, right? And we get a horizontal compression if b is greater than 1, right? So that's kind of the reverse of our intuition. You would think that, oh, because we're multiplying by a number larger than 1, it should get larger horizontally, but it's actually the reverse. We multiply by a number inside larger than 1, it causes a horizontal compression. We multiply the inside by a number between 0 and 1, it causes a horizontal stretch. And then if b were negative, again, you consider it, you work it as if you're working with the absolute value of b times x. And then when you're done, whatever result you get from your horizontal stretching and compressing, you flip it horizontally over the y-axis. So I know that's a mouthful. And I think that brings us to all 10 of our transformations. This one very easily causes information overload. I want to say that these concepts are not difficult. They are simple, it's just not easy. Simple in that the complexity level is low, but it's not easy because it's a lot of information, right? So that's the challenge. That's the challenge that we have before us. And the proficiency and the level of being comfortable comes from repetition, right? The only way you really get comfortable with this stuff is through repetition. I think I'm going to go ahead and stop here. We worked this one earlier with my other group. Let's look at it really quickly. So use the graph and the figure whose equation is not given and sketch the graph of each of the following. So if we multiply the inside by a number between 0 and 1, inside is going to cause a horizontal change. Because it's between 0 and 1, it should cause a horizontal stretch. So this one causes a horizontal stretch. This one should cause a horizontal shrink. And then for this one, we take the result and flip it horizontally, okay? So a horizontal stretch by a factor of 2, you see it here. Okay, and then this one, horizontal compression by a factor of 0.5. And then this final one is the same thing, but now you take your result and flip it horizontally. So the y values stay the same, but the x's go from positive to negative. Okay, and I think that's as far as we made it. Actually, we did this one as well. But I think we're out of time, so I'm going to leave this as an exercise. I'm a little nervous asking this question. I feel like there should be questions, but it's okay. Just do the best you can. I do encourage everyone to work together. Are there questions? All right. So let me go ahead and load a copy of this for you to access. So you should be able to access a PDF version of everything that you've seen from the beginning of the semester up until now. And basically at the end of each session, I load a copy of the PDF. Just do your best, right? Just do the best that you can. Do what you can on your own, work together, do what you can working together. Make use of the tutors. You've paid for the tutors already, right? That's part of your tuition. So, you want to sit down with them. If there aren't any burning questions, we're going to end the session here. And from one beautiful mind to another, enjoy the rest of your day. Stay dangerous and peace. Yeah, let's see. That's the chat. Yeah, no worries.